Let me introduce the reason why we are here and our excitement in organizing this, this session. First of all, my name is Rafa Muñoz Carpena. I'm a professor at the University of Florida in Gainesville. And a couple, actually more than a couple, I should say probably 4 years ago, one of the members of the society, Wayne Skaggs, approached me with the idea that we were getting to a point where the society was financially sound, and there was this opportunity of special initiative funds, which essentially were small amounts of money to promote new ideas or groundbreaking themes across the society. And we were lucky enough to get one of those initial special initiatives. And the topic that we selected was one that I really believe that is central to our society. We are uniquely positioned as engineers in the midst of food, fiber, and energy production with a view of sustainability of environmental resources. So right there is where the topic that we are going to introduce, I think, is very well positioned. The topic of ecohydrology is kind of it means many things. It's, you could say, perhaps, is it a buzzword, would be the question. And I think it means many things to many people, starting from purely semantics, you know, ecology and hydrology. But there is a lot more to it. I think one of the very important things to realize is that the interface between water, ecology, and more people is a complex, an extremely complex interface, okay? So we no longer can study this system in its individual parts. We really need to take a comprehensive view of the system, understanding that every part is linked to each other and the feedbacks are inextricably joined, so we cannot really separate them. So new tools, new techniques have to come into place to understand how the systems react to future scenarios, what are the projections, how manageable are these systems, which in fact understanding this complexity is probably impossible, but at least can we get a shade of what is their behavior to be able to manage them. And I think that is a huge challenge where we engineers on this field are very uniquely positioned. So that was the motivation of this session. And then a group of people started thinking about this, which are essentially the moderators of the session that you're going to be seeing today, and others, where we met as a committee trying to identify who could be our starting person on our keynote presenter in the session. And of course, we were incredibly pleased to be able to get Professor Andrea Rinaldo. I'm going to introduce him as our keynote presenter, and he will be followed up by a set of also amazing invited speakers that will be introduced by different moderators throughout. And remember that one of the key purposes of this session was not just to have a regular lecture session, but also brainstorm about opportunities for the society around this topic. So I asked each one of the presenters to give us, at the end of their presentation, some thoughts about future trends or challenges that there is around this topic. And also, the speakers were selected around the idea that this theme is many things to many people. So I really wanted to capture different views about what the topic means. So you will be seeing a sort of a survey of different approaches to the concept, which are all complementary in my mind, and really build a whole perspective of what this might mean to us. So from the individual presentations, I hope that we will get a lot of exciting challenges and opportunities, and then we'll wrap that up in the final panel where the speakers will sit together with all of us, and then we can start discussing, brainstorming a little bit about what it means and what kind of opportunities we have. So that's the overall program that we have ahead of us, busy as it is. And the first thing I want to do then is introduce our fantastic speaker that we have here today. Let me just, here it is, okay. So Professor Andrea Rinaldo is very well known, I'm sure, by all of you. He's a professor currently at the Lausanne School of Engineering, Polytechnique in Lausanne in Switzerland. He's been a professor in the Italian system for many years and has held other positions, including University of Padova in Italy, He moved then to, he held 2 visiting professor positions at the Massachusetts Institute of Technology and also at Princeton University, where he developed some of the amazing ideas that he's going to be talking about today. Then he moved to the Lausanne Institute of Technology and also have some adjunct positions elsewhere. He got his degrees, his PhD from Purdue University in West Lafayette in fluid mechanics, and also bachelor's and master's in the University of Padova in Italy. He's received almost every major award related to water from the key societies around the world, including the Hydrological Sciences Award, formerly the Horton Award from the American Geophysical Union. He's a fellow of the American Geophysical Union, the Dalton Medal, the equivalent in the European Geophysical Union, ERC Advanced Grant Fellowship in 2008, the Borland and Hydrology Days Award in Colorado State University, the Prince Sultan Abdulaziz International Water Prize, a huge award, and finally the Luigi Tartufari International Prize in Rome in 2014. And this is just but a few that he received. He's also a member of many academies, including the Royal Swedish Academy of Sciences, Italian Academy of Sciences from Venice and Rome. He's also a member of the US Academy of Sciences, US Academy of Engineering, and he also holds honorary degrees at doctorate honoris causa from in Canada. He's editor of Advances in Water Resources and the Proceedings of the National Academy of Science, PNAS. And he's published over 200 high-tier index journal papers. His citation record is amazing. It's over 1,100 citations of his work. His H index is stratospheric, 56. And finally, one of his papers alone received over 1,300 citations. So I think you will agree with me that we couldn't have a better person to get us excited and interested about this topic. And with that, I'd like to introduce Professor Andrea Rinaldo, the one and only Professor Andrea Rinaldo. Thank you.
Now, but I certainly disappoint you after a presentation of this kind, especially because I'm particularly stoned because I arrived late yesterday. But thank you so much, Rafael, Professor Munoz-Carpena. Thank you so much for the organizer for this invitation, which is very dear to me, speaking about things I care very much for. And perhaps a few explanations. The title of the talk is slightly technical. I could have reversed that. So my title is The Metapopulation Capacity of Evolving Fluvial Landscapes, but it could have been more easily, perhaps more accessibly, titled River Networks as Ecological Corridors for Species, Populations, and Pathogens of Waterborne Disease, which is what I do for a living in Switzerland and still with a foot in my alma mater in Padua. Now, the picture you see is a picture I took of the banks of a Meghna river in Bangladesh, near to the site called MATLAB, which is one of the international, not MATLAB, the code, but MATLAB, the place where you have International Center for Diarrheal Diseases. There's a place where cholera started. Now it's endemic for like hundreds of years. In an evolutionary sense, the pathogen developed in that area. And it is somewhat emblematic of why engineering and perhaps the mission of the American Society for Agricultural and Biological Engineers matters, in the sense that you're looking at quantitative evaluations in the engineering sense. If you please, von Karman, the great fluid mechanics professor across the two wars, then made it to the US, said that the distinction between science and engineering is that science studies the inner workings of nature, and engineering studies what is not yet. So you're looking at the effect and looking forward to what can be done for the betterment of society, for bridging the gap between the North and the south of the world, which is something I care very much about. But the picture is still meaningful because I took the picture and I was wondering, will the young guy catch cholera? Cholera, the Vibrio, I mean, one catches cholera if ingesting not a concentration, but a number of Vibrios exceeding a certain threshold depending on the size of a person, etc. And if you figure, what are the odds that the guy will catch it? These are the odds of predicting the concentration in a specific point in space and time of an otherwise fluctuating value. And the challenge to engineers and to our mission is that can we reduce the gap? Can we narrow the gap? Can we bridge it? Can we predict somewhat reliably whether the young guys catches cholera or not? So this is with that in mind, the quantitative aspect, the predictability of these things, I'd like to show what the plans is. Why focusing on one specific ecohydrology, as Rafa put together so nicely? To me, it means water controls on biota. And of course, not everything is water controlled. Think of vegetation, think of rain-fed agriculture, for instance, but many, in fact, ecosystems are water controlled. And in a sense, you have to narrow down to some specifics, and I will be focusing on river networks and why I presume they are important in the quantitative evaluation of ecosystem services. I'll be talking about river networks then, and the ecosystem embedded into them. To do that, I will have to go briefly through something which is very dear to me, and I'm pleased to acknowledge my co-author, my longtime friend, Ignacio Rodriguez Iturbe from Princeton University, with whom I developed every single thing that is in here. We've been working together like for 30, 35 years at this, 30 years at this point. So we're talking about what shapes the form and the function that we see in the fluvial landscape and why they are so important. Why the purported universality that you see in the fluvial landscape teaches a lesson of general nature. And the second, some spin-offs, essentially what ecologists would call directional dispersal, and spatial ecology. So we're talking about the evaluation of fluvial ecosystem services, biological invasions, population migrations up to a certain point, and the transmission of waterborne disease. I would like to convince you that there is a consistent, coherent theoretical framework, a conceptual thread that joins methodologically and practically the above problems. And so in essence, if what hydrology applied to ecology is all about is floods, droughts, and a fair distribution of water, I am interested in a fair distribution of water in a quantitative sense, if you please. So let me start from a few ideas on why this somewhat changes the ball game of sustainability. The idea is that the architecture of contemporary development thinking is stacked against nature, according to foremost economists like a good friend of mine, Partha Dasgupta from Cambridge University. What it means is that if you measure the well-being of a society from indicators like the gross domestic product or any ad hoc indicators that you see that the growth in wealth, the growth in indicators of society's wealth doesn't take into account the so-called per capita, properly discounted wealth of an individual. In the sense that GDP essentially doesn't discount properly the environment and the ecosystem services that can affect dramatically those measures. Like, think of the example you see here from Edward Barbier. There was a comment published in Nature in November last year, there have been a few others following, on the mangrove swamps disappearing in Thailand to make way for commercial centers and the like. The point is that if you drain a wetland and you make a commercial center, and then from that point on for years, you're going to see in the GDP of the region, whatever you want to call it, the effects of that commercial center. But you'll never be able to account for the biodiversity loss you have because you cannot quantify it in economic terms. So proper depreciation of natural capital is a vital thing, and one of the main responsibilities, because we as engineers, as environmental and biological engineers, although I'm a hydrologist, I keep saying we Swiss when I'm at Swiss meetings, but I'm not, I'm Italian and probably so. But we environmental and biological engineers, we have a responsibility in that we must be able to quantify those values. And in that sense, the analysis by the French economist Piketty was very important, Kuznets-like curves that would assume, because of the economic rationale of the, in between the two wars, that economic development would inevitably bring social equality, proves out to be highly misleading. Because if you take into account in the growth of wealth at the nation's level compared to the growth of individual levels, it turns out that in reality, inequalities do not disappear with the amount of wealth. And one of the things is that you have to find the social worth of entire environmental capital. That's one of the key issues. So the take-home message, in my view, is that you have to think seriously on, can we evaluate ecosystem service? Can we put a price tag on ecosystem services? Prior to that, you have to be reliable in predicting what these are about. And that's why I presume that river networks, I'm getting to my turf, actually, are important in my view. Why? Because why is nature reproducing the same structure everywhere, regardless of soil, climate, vegetation, exposed lithology? Why, if you take out the scale bar on a river network, like in that case, I keep telling for sentimental reasons that the old map, the first DTN we extracted in a place, I took on purpose out the scale bar, because just by looking at that, you cannot tell whether that is the Amazon or this is a creek nearby. Maybe if it is tidal, of course you could, like in the case of Mississippi at this point. But in general, why is nature producing the same shapes at whatever, regardless of the scale we are discussing? And that became perhaps center stage in a debate larger than hydrology and geomorphology like 20 years ago, because of the remarkable capabilities we have acquired to remotely acquire and objectively manipulate accurate description of natural landforms. From a scale of a meter to the scale of thousands of kilometers that you have in there. I'm sorry, I was going the other direction. So for the time being, that's one of the technical things, not earth-shaking, of course, but quite important. What is the master variable in describing the aggregation structure, which we find universally true in the fluvial landscape? And again, I'm not claiming this applies to any possible ecosystem, but fluvial ecosystems are important because in the fluvial basin, much of biodiversity is harbored. And one of the questions that you have to ask on a quantitative basis, would large-scale water resources management plan include biodiversity preservation in the future? Are we capable of doing that? Can we predict why hydrologic controls can mitigate disease, in a sense? Will we be able to predict effects of development of irrigation works? For instance, typically in sub-Saharan Africa, we would have lots of irrigation projects that clearly develop the GDP of those areas, at the cost of a higher major increase in the prevalence of schistosomiasis, for instance, which is a debilitating parasitic disease. In every GDP, the irrigation project will show up, but not the cost, the social and human cost of a loss in the development capabilities because of the debilitating features of the disease for young kids, for instance, because that doesn't show up in any balance sheet. So these are the kind of questions that we need to ask. And back to the technical stuff, what you have is that essentially from digital terrain maps, which you have almost anywhere, from a scale, say, for a meter to the scale of, that could be free, like the scales of 30 by 30 meters. You can calculate the drainage directions by simply calculating steepest descent, topographic steepest descent. So essentially, you tile up a landscape, the greater the relief, the more precise, of course, it is. But now you go to precisions in the altitude once you filter vegetation, which are the order of a few centimeters. So essentially, you say the flow direction, what gets out of a flow from that particular side will go to your nearest neighbor, what you see in there. So you can calculate total contributing area. Well, the obscure expression in there is simply saying that if you're sitting in a place and you have a few guys draining onto you, they bring their own total contributing area, and one is the pixel unit area, like 30 by 30 meters or 1 by 1 meters, depending on cases. This is a master variable for measuring the aggregation structure that you have in these systems. And what you're seeing here looks like a picture, but it's not. It's a digital terrain map taken from a LiDAR or LIDAR, as you want to call it. This is a laser-borne altimetry in which vegetation has been filtered, color-coded for elevation. And the blue seems like this is, by the way, this is a part clearly because of the ebb and the flood channels is clearly a tidal landforms. But you see like the coexistence of different kind of networks in there. Now, one interesting thing is that the distribution, these are empirical data, and they are robust, they are universal, that you see in there. They show that there are the signatures of critical, self-organized criticality of a system. That is, the system, regardless of the initial conditions, regardless of the tuning of the million of parameters that would generate the way little reels would develop into larger streams, etc., regardless of the exposed lithology or whatever, climate, precipitation, or whatever, the system would aggregate inevitably along a system, rather than being, it's at the edge of chaos, but is the opposite of chaos. That is, regardless of initial conditions, frustrations of a parameter, type of parameter, the system would inevitably do the same thing. And that happens, and the distribution of those areas, that is, you close your eyes, you point your finger at the map and say, what is the probability distribution of total contributing area at this point? This is the same in every single fluvial basin that you can figure out in the world. That's the universality of the patterns are their own importance. And then we have in our arsenal of tools some particular structures like the Peano network. Peano is a mathematician, is an Italian mathematician, in fact, of the 19th century, taken as an idiot by his fellow mathematicians because he wrote a paper called Over a Curve That Fills an Entire Plane. He had anticipated what we call now the fractal dimension, something which was popularized by Benoit Mandelbrot, who in fact popularized the work of Giuseppe Peano as well. That is, if you take the measure of the length of Peano basin, that as soon as this iterative construction grows, this is in fact equal to 2. That is, the length is a surface in the end. It fills the entire plane. It wasn't a wrong mathematical result. It was a very profound thing, way ahead of its time. Now, the interesting thing is Peano is not statistically self-similar. That is, the part and the whole are not similar, like in the case of fluvial basins. You extract a sub-basin, you compare to the whole, and the statistics are matching, except for the finite size. Now, in this case, it is exact, because by construction, that you see a trace in there of a, I think I even have, lovely, whatever. I even have a pointer. Thank you so much. So by way of the catchment is constructed, that's what you're going to have. So it's a particular structure. And does it look like a river network? No. But it has two qualities. From a topological viewpoint, topology can be a very insensitive indicator on how a tree-like or network-like shape behaves. Topology, I mean bifurcation structures, length structures, that is the way the system develops. Like the bifurcation structure you would face if you move, for instance, along the backbone of a network. And the other thing is that it can be analytically treated. I'm talking to the engineers in there. So there are quite a few analytical results that can be exploited. If, for instance, last but not least, the fact that the width function, that is, number of sites equally distant to the outlet, are mapped into an exact binomial multiplicative process. And there are optimal channel networks, of which I'll be talking soon. That is, there are constructions on which Ignacio and I worked since the early 90s, in fact, which we've thought like an exercise until we realized that the fact that a stationary solution of a landscape evolution equation in the small gradient approximation under a set of unavoidable constraints like reparameterization invariance are, in fact, the solution of a general problem. So this is not like an exercise, but the fact that these structures reproduce all scaling exponents seen in nature in a huge archive that we now have about the structure of that, this is the way you can generate actually structure which are fluvial-like in every possible sense, topological, metric, etc., in any domain you want, which is important for ecological processes. So what you do, again, the total contributing area at any site, ASABE, meaning you close your eyes, you point your finger, and you have the total contributing area like you have it if you have it in the map. Okay? Now you sum all of them together with an exponent, which is less than 1 for physical constraints, and you find out that the shape, if you want, the functional, which you call H sub gamma here, that is the configuration of a system that minimizes total energy dissipation, which is the exact result. So essentially, the aggregation structure dictates the areas at any point, and it dictates a three-dimensional structure of a catchment, and that can be found, in a sense, in any possible domain, through an exact statement as a feature. And not only that, you can also show that because of the nature of that exponent, you can show that every tree is a local minimum of total energy dissipation. So in the fluvial landscape, loops are now created like in the tidal landscape for very, very serious physical things. I'm sorry for the long introduction because so the idea I wanted to convey is that when it comes to networks, there's a lot that can be said, especially to networks that apply to the particular landscape evolution equation that dictates how channels form. So in the three networks you see in there, and that's the last thing I'll be talking about network-like, you see you have like a spanning tree, topologically indistinguishable for real networks, and yet very different if you look at that, both metrically and from other points, even visually, and OCN, a local dynamically accessible minimum over global minimum which doesn't belong to this world. So essentially, the key point is that dynamically accessible states, locally accessible, are the ones we'll be seeing in nature. Long story short, we know why in nature we find always the same shapes. So we're ready to move on to some of the quantitative experiments, and the idea is that you want to study spatial ecology of those structures. Sensu, Tillman, and Careva, of course, the famous spatial ecology book. So essentially now every site, every pixel is the site of ecological process. And we want to study in the first place how this is just the very structure, the very dendritic connectivity of the ecosystem, whether or not it has an effect. Because we presume there are empirical, theoretical, and now experimental results that show this important one. Not only that, this is greatly constraining the uncertainty you would expect in any theoretical model, thereby suggesting, somewhat strongly in my view, that they can possibly be within the aim of agricultural and biological engineering for quantitative purposes of evaluation of ecosystem services. So that's how the system works. And to explain how the system works, you best get into a model which is called the voter model in the social sciences. Suppose you have like a lattice of sites, like a regular lattice, that is every single site has 4 neighbors, nearest neighbors, or a site in which the connectivity comes from a network. That is, you can have a guy near you, but very far away because the connection pattern goes through the network structure itself. So your neighbors are dictated in one case by a network, in the other case by any possible physical proximity. Now what you do is that suppose you have in every node, it's an individual-based model in the sense that you assume that you have a specific color generated at random in every node. Now a color is a political opinion, for instance, in the original voter model. But of course it has a very important implication for ecology, as I'll be saying in a minute. So you have a palette of different colors, completely random, or you can start from like a few, like in this case here, you can see what happens with a different, like a small number of individuals, and you start evolving the game as you see it. So the game proceeds as follows: you hit a node at random, and you kill the color you have. That is a political opinion. And you assume that at that point, the opinion you're going to have in this point is just that of the majority of your nearest neighbors. Details aside, because if you have like 2 equal ones, you choose at random, okay? Then you go somewhere else, you kill the opinion there, you do the same, and you keep going. Now, if you do that, there is a major ecological assumption, it's called the neutral assumption, that you assume that no political opinion is stronger than any other. The neutral theory of biodiversity assumes that Stephen Hubble, formerly at Princeton University, assumed that, which is anathema to many ecologists, assumes that the vital rates of every species, of every individual, of every color are the same. No political opinion is stronger than any other. You may have objections at this point. We'll get back to that later on how you relax that. But the point is that if you do this, what you have is that, don't worry, Raphael, I'm get carried away. When time comes, I'll stop. So because I kind of love to be unstructured in my presentations. So what you have in the system is that if you do that, and you start from a place, in the end, you know exactly what's going to happen if nothing else is done. That you're going to have like a monocolor, just a single color. The one was present in the beginning with the highest abundance. The number of sites with large number of colors, in the end, obviously will win, theoretically. Now, here's the modification. With a certain probability, which is called the diversification ratio, every so often, like every, I don't know how many generation times measured in terms of L by L square, well, L is the side of the thing, you just, you say, okay, you kill the color, and you assume one color that's not present in the initial one, which is like an immigration of new species, speciation in evolutionary sense, or immigration of species that were started before. If you do that, the result is very complex. It's what you see in the process here, regardless of the values of the parameters. But most importantly, what you see in here is the fact that you see, even visually, look at the distribution of colors. The only ingredient that is different in this case is the network structure in one case. So it's directional dispersal. Your neighbor is not your physical neighbor geometrically, but it's your neighbor in a network sense, whoever is connected to you at the nearest neighbor level. What is fantastic in this case is the fact that this result, and I'm pleased to quote Professor Munaparakul's work when he was a PhD student, most brilliant one, I have to say, now he's a professor in Florida at Princeton University. The remarkable feature of this result is that it resists, now this is individual-based model. You can make it a meta-community model. That is, you can have in every node not a single individual, but a population, and not a population, but a community of populations. You can relax the fact that you can have in this place not only the nearest neighbors, but perhaps a kernel of influence, perhaps the mean field. That is, you choose simply the most abundant in the entire lattice of things, and the results will be the same. Directional dispersal, and the shielding, which is naturally produced by the river networks, the source areas distributed almost anywhere in the system have a major impact on the biodiversity of the structure of the system. And that, of course, can be studied in terms of a persistence time distribution, which depends on the nature of the spatial interactions. In fact, on a line, you'll be much better off than in a network, than in a two-dimensional setting, but in a three-dimensional one, than in a mean field one. And you see, the ecological counterpart, for instance, if you take the breeding bird spotting sites, it would be like studying presence and absence of birds that you have in every single red dot that you have in the map of the US. It's a bird spotting, in fact, site. And what you have in the system in there, it's the fact that the duration of the thing is a simple local extinction of a species that can reappear at a later stage that's properly coarse-grained in time. Now, interestingly, to verify the theoretical assumption, it would be very hard to convince ecologists, especially field ecologists, as you know perfectly well. But one thing you can do experiments of that, and that's what we did in my wet lab, which I put up in Lausanne, in which now we take physical nodes, like places of this size, in which you put like 21 species of protists, detail can be given, and so then you can make them to evolve, and you have the system in ecological time series, and you can have the ecological structure that's studied. You can arrange them with connections that are network-like or lattice-like. And you can replicate as much as you can, as much as a graduate student can survive, actually, but it was a significant replication done. And the result is what you see in there. The higher connectivity, I mean, if you're open to many interactions, you don't have shielding, you don't have hiding away, you observe features that is source areas, like Bill Fagan, the field biologist, finds in source areas are disproportionately important to local species richness, for instance. That's something which you can find even in an experiment done in the lab with ecosystems at that size, like you see in here, like 9 by 9 sites of this kind. And most interesting, perhaps, because I'll be getting to Mississippi, jumping from this size to the Mississippi River in a second, most interestingly, if you assume that the habitat capacity, which is essentially the amount of medium that you can place in the system, conserved everywhere, if it is uniform or random or hierarchical, like you would have in a fluvial system, has a major impact, in fact, on the structure you have. Conforming to common sense, because geomorphological relationships are well known in the system. So I'll be moving on river networks and biodiversity, and what's the connection now? I'm talking about something which is highly abstract, that is something which comes from theoretical models, some which is, for some, highly abstract as well, because it's experimentation of this size, replicated many, many times, but with a real ecosystem with 21 species inside, in which you measure in time and painfully species diversity. But what's the message that carries through? That is a system that are made up of nodes and connections, network science, if you want to call it in a sense, are extremely important because they grant certain features naturally because of the connectivity structure that the system has, which are quite important. So essentially, the coherent framework I was talking about biodiversity, about population migrations, about disease transmission as well, is the same framework in models of reactive transport over an environmental substrate which is connected by networks. So you have nodal reactions, whether chemical, physical, or biological in the nodes, and you have transport connectivities between nodes. And this can be done for individuals, it can be done for species, it can be done for meta-communities, it can be done as several things. So let me talk about Chot's work, in fact, and then I'll be talking about the recent work of more theoretical nature. I hope I won't use you that, but I'll be delighted in following up in any manner. So these are the typical structures we can discuss. So it is, you have a real river networks in which at every junction you put a node. You have a piano network, which is suited for analytical solutions or optimal channel networks or real river networks in the system. And a good example, which is quite appropriately, in fact, in this here because of a nearby Mississippi, is of course the Mississippi-Missouri River system per se, the whole thing. The maps you see in there, this is done by the great study by field biologists, especially Bill Fagan again. He was talking about the presence of absence of fish species at different sites, at different positions within the Mississippi-Missouri River areas. So LSR means local species richness. How many? By counting not the abundance, which is complicated, by presence of absence, which is way more reliable. You get, I think it's 433 fish species overall. The total diversity which was in the system means like 850 sites on which directly tributary area was available. And you will see in there, it doesn't take a statistician to see if there is some pattern in there. And the pattern is between local species region and this AARP, which is annual average runoff production. That is how much the cubic meters of water went by that particular cross-section, depending on the hydrology of the system. And it's interesting to exploit whether the network structure could do something good for us. And that's what the model that Chot put together in the Princeton group, and I was probably part of that, goes as follows. It's not that far from the model I've talked about the Norton model. So essentially you assume that in the beginning of a game, you have at every directly tributary area, that is the sites in which you connect in the system, you see how complicated it is, in fact, from the picture you see above, is completely saturated. All resources are taken. So essentially what you do, you kill a fish unit in a place, and you free resources. How you assign those resources depends. Depends on what? It depends on a certain probability that from any other site, whether far or near or everywhere, gets into the place and colonizes it. And that depends on the kernel of dispersion. In the case I showed you before, the Wörter model was simply nearest neighbors. Here it's more complicated. Why? Because fish moves. There are attributes. I could talk forever about that, but it's the messages I would like you to keep. But one of the messages that for ecologists, as I told you, the neutral assumption was assumed as anathema at a certain point. But still, you have to realize the neutral pattern doesn't require neutral process. So these patterns have a generality of their own, which you could speculate for a long time. The second thing is that you see in there is that you assume that essentially the pool of species you can draw upon, given the distance, which is a property of a fish, active dispersal, of course, still limitation, if you please, with respect to many other species, but still revealing because of the data set you have, and can allow you to fish depending on the habitat size, which is essentially a measure of a directly tributary area. Again, hydrology. Again, geomorphology, because its total tributary area is how the system is shaped and how annual average runoff production is done. Long story short, Professor Munabrakul did a fantastic job in matching the presence of abscess data, as you see, as a measure as a distance to the outer, the pretty stringent thing, etc. And the alpha diversity produced by the model, that is a number of species simultaneously occurring in a place measured along the Mississippi, starting from New Orleans to the sources, wherever they are, works beautifully well, with the exception of sources highly urbanized places, and of course natural boundaries which you have in the system. But these freshwater species cannot exist when you have salt water intruding in a specific form. So I jump from a scale of this size to the scale of the largest river that you have in the system. So you have a good point in assuming that perhaps there could be a message of general nature behind these. One note, which I love to measure, is that if you put constant habitat capacity for every node of the Mississippi, Missouri, regardless of the total contributing area that you have in a site, which you can measure directly without mediation, that's what you would get. It's a completely different result. And that echoes the results that we would get in the small laboratory replication if you take the same amount of medium everywhere, but in one case uniform, in one case randomly distributed, in one case hierarchically distributed. It's the same result, actually. And that allows you to talk about the probability, the dispersal, the sensitivity of a system to the disappearance of species, some of which we haven't really studied so far. This is called beta diversity. That is, if I have in this particular patch a certain number of species, at a certain distance measured along the network, how many species that you have in the focus site still survive? The survivability of that is a measure of the biodiversity. And then, of course, because then you cannot tag a particular fish. Its presence of absence, you have a number. You don't have specific vital rates. Of course, you have differences. And yet, at the scales of thousands of kilometers, you have patterns, neutral patterns, which remind extremely well, and very well so for engineering purposes, the behavior of the system. And here I'm getting to the relatively late. I think I have, do I have 10 to 15 minutes? Okay, whatever, but then I'll stop up. That's a work of a great ecologist, Ilka Hansky, the guy who got the Carrefour Prize, actually, which is one of the highest distinctions in geosciences, ecology, invented a concept of a metapopulation capacity of a fragmented landscape. What was the idea? I will explain it in a second. The idea is that there are landscape matrices that describe how species can assemble in a different place. He thought initially of a fragmented landscape. The idea, sorry for the technicalities, but again, I think it makes sense in the engineering meeting to recall why we are there. So essentially, that's what you study is an equation in which you study the evolution of a probability of a focus species being present at the patch of the site I in time t. When that probability goes to 0, is the extinction, of course. Pressed by different forces. One is the extinction forces, characterized by the small e event that you have in the system, and colonization that comes from any place you could actually reach through there. Characterized by dispersal distance, in this case 1 over alpha. Dij is the distance between any j site to the focus place I, and you have essentially immigration, or immigrations, speciations in this case not represented. For a single species in that case, represent the process of a balance of extinction and immigration effect. And the parameter delta, which you see in there, is the A over C in the system. So essentially, a network now is a set of n nodes. For each of them, you have one equation, the probability of survival at time t of that species there. You have vital rates in a place. And what you have in the system is that then thereby you can study the stability of the system itself. That's something that engineers long knew. And essentially, so you study whether the probability equal to 0 of the extinction is stable or unstable. So the state characterized by extinction, pi equal to 0 everywhere, is the global extinction equilibrium of the model, even in the face of breeding birds spotting. In a place, you can have a species disappearing, but a few years back reappearing. But if you take the integral of what happens over every single node of a continental thing, if at the entire continent scale the species disappears, it's really gone. Now you want to study the stability of that. It's a tool that, well, that's perhaps my bringing in fluid mechanics is pretty clear to me how you do that. But you can study the exchange of stability. So you can study essentially a determinant constructed with a certain derivative. It's called the Jacobian of the system, and you can study its eigenvalues in the particular thing. So if P0 is stable, if the nil probability everywhere is stable, no species can exist. The focus species goes extinct. And in some other cases, where this becomes unstable, and that happens when a particular eigenvalue of a matrix called the landscape matrix of Hansky here modified to have essentially not for a fragmented landscape, but every single area from which you can come has the same size in the network size. That was the innovation of the paper we published. So it's a particular matrix, and for those technically inclined, now essentially every row of that matrix is the sum of e to the minus alpha dij. That is the distances exponentiated that you have from a place to any other place. It is a positive, non-reducible, positive definite matrix, so it applies to theorems like Perron, Frobenius, etc. So you know that there is a maximum eigenvalue. You know the structure of that, and you can find that eigenvalue, which is non-nil. And what is greater than being? This is called the metapopulation capacity, which is the measure of the entire landscape, essentially. So see what happens in the process of searching an optimal network commanded by physical processes. That's exactly what you have in the system. So you see, what you do in finding the minimum, you typically accept any changes to get rid of a role of initial condition. Then you start accepting only changes for lower energy dissipation. So you get the blue line in there is the energy of the system, and as soon as the energy goes down, you get very reasonable shapes. Now, in return, what you do in the system, you calculate the metapopulation capacity of a system, and you then see that this goes up. Now, is that an important result? Well, in a sense, we believe it is, because this is not, this is talking about, oh, this is only one species. So how can you tell about biodiversity in there? And by the way, once you have a metapopulation capacity, you also have the probability of extinction, per se, that you have in the place, which you have the different colors. The closer you get to the red colors in there, the stabler you are, the higher the probability of persistence, and the bluer you are, the closer to extinction you are. So you see, as the network evolves, only prescribed by physical constraints, you get as a bonus viability for species persistence. So essentially you see that physical evolution in some cases doesn't prescribe any kind of biological optimality, which biologists don't like actually. You simply get it. And I think it's an important result. Now, well, that's how you do that. Essentially you study the structure of those matrices. And why we believe this is an interesting result? Because in fact, this works in a metapopulation concept, it is a single species, but it can be generalized to produce biodiversity structures, as Hansky himself found out. For instance, you can sample, still you put no interspecific interactions, but you can sample different values of a dispersal rate, which is here, the average dispersal rate, which is certain biological features of a system, or of a vital rates, and you get that inevitably the type of network that you have will do the job better than anything else. Well, in the last 5 minutes, I'll show you how this can be generalized. This was the key message I wanted to secure. And in the last 5 minutes, I'll be showing you what are the possible consequences and the way forward, perhaps. One is metapopulation persistence and species spread in river networks. That is, what you can do in a system like that, you can study now something which you have metapopulations, but of structured populations. For instance, juvenile and adults, with different mobility, in fact, between the different parts of that. Well, salamanders, for instance, I'm referring here to the classic mark recapture study of Campbell Grant in the rivers of Virginia, for instance, which have juveniles have a high capability of crawling outside the river network, connecting perhaps different streams, whereas adults are typically more sessile, that is, more local, stationary. But it's not necessarily true. That one of the things in ecology was known as the drift paradox. Why in a system in which you have a drift that takes you downstream and no motility, for instance, no locomotion intrinsic to the species at certain stages of life, why don't they disappear everywhere? Well, insects, for instance, they are typically mobile along the network in the larval stages, but can fly back upstream in the mature stages, but not necessarily. Parasites, for instance, can have intermediate hosts that are typically very slow, very local, and mature hosts that are, in fact, very mobile, like fish. The idea is that there is a system in which, don't look at the equations, but it is that you have two equations, the rate of change of a balance that you have. Is not rocket science, I mean, it's just standard, but it's the meaning that I want you to have. The rate of change of juveniles and the rate of change of adults respects a balance, which is something that every engineer knows how to construct. Mortality, M of Y and A, possibly density dependent. You have the transformation of juveniles into adults, And you have natality, which of course depends on the number of adults reproducing in the system. And then you have mobility, where you can come from, the local mobility, etc. And it can be different from adults to juveniles. Long story short, P and Q can be characterized in different species. And you can study the stability of the system as well. So you can find the equilibrium in which you have no juveniles, no adults, but the extinction equilibrium. But now, pressed by a number of, the exchange of stability will tell you whether population can persist, given the specific features. Again, no interspecific interactions yet, but this can be done. And the idea is that even in the case you show that whether or not you're moving on a one-dimensional system, on a two-dimensional system, or on an optimal network, you have a very different region of stability. So the idea on how you make connectivity work, think of you guys, the agricultural engineers, think of irrigation schemes, for instance, have a complete different, extraordinary impact on the probability of survival of species, including parasites. And that's why you empirically find that the irrigation developers in Burkina Faso brought up the incidence of schistosomiasis by orders of magnitude anywhere because of irrigation structure, and that's empirically documented. So you can study salamanders, you can study zebra mussels of the Mississippi-Missouri, again, the Mississippi-Missouri River system, which was another unfortunate case. The condition for persistence of a species is the condition for biological invasions. Now, a few Russian cargo ships brought in the ballast water, brought some veligers of this zebra mussel, a terribly infectious, you know it perfectly well, many of you, in the Great Lakes region, that started then spreading through the Mississippi-Missouri River system in very strange ways, because you see even yellow dots very far away. So in this case, you can study not only that, you can study the stability of the system, the consistency. So big deal if you tell that ex post, well, I knew that it was invadable once it happened. It's different. Here you can get from the eigenvector corresponding to the leading eigenvalue, you can get the geography of the early phases of invasion patterns. Or in some cases, you can explain why different networks have different ways of explaining invasion patterns. Why you have certain things in which, in the Mississippi, Missouri, you have a zebra mussel propagating in a certain place, and then over way up in a lake in Idaho, you start having a zebra mussel. Because a guy takes the boat with some veligers on it, jumps it on the cart, and takes it, drives it directly to the other place. So you have to take into account several mobility networks, pretty much like you do in infections of several kinds. And you can simulate that fairly well. And last thing, in the last minute, I'm not going to talk to that, I knew that, the framework works beautifully well in explaining pathogens of waterborne disease. I've been in Haiti quite a few times, in fact. The same framework allows you to study, for instance, epidemic cholera. Nodes are places in which you have susceptible, infected ones, and concentration of bacteria. And you can study how they interact in the face of a place. And then, by the way, one thing is studying the diffusion of networks, and one is seeing the disease in action, which is pretty disturbing, as you guys have been in the thing, etc. But what you see in here, these are the total cumulative cases which you have in Haiti in the famous 2010 epidemic that followed a disastrous earthquake. It killed 300,000 people in the poorest country in the world, in which there's no sanitary infrastructure, there's no police, there are no roads, there's nothing in there. And on top of that, cholera was planted by UN peacekeepers because it's a Nepalese strain of a disease. The country has been cholera-free for 200 years. Isn't that deeply ethically disturbing? But what you see if you take the cumulative things that you have in the system, what you see is that you see the structure of the networks. You see two networks in there. One is the river network along which, and you have empirical documentation about the pathogens, the vibrio. The greatest production of vibrios is the intestine of a sick. Because then the concentration of pathogens injected into the environment, untreated, is orders of magnitude larger than any quantity that can survive ecologically, the vibrio, etc. And the other one is human mobility. Why? Because if an asymptomatic infected guy moves to a place and sheds in the place and gets back, the pollution stays in there. And the same if a healthy guy goes to the wrong place, drinks the wrong water, and moves back. Human mobility patterns can be dealt with in this fraction. This is what we can do now, and that's absolutely the end of it. By the way, so that's what we do. In fact, they recorded weekly cases, department by department, and simulated ones. And it's exactly the same features as I told you. You can have a geography of a disease, and you can even also have something which I won't talk because I swear it will be too much. The so-called reproductive number. The number, in ecology terms, the number of daughters produced in an entire lifetime of an adult mother. Reproductive number larger than 1, it means that a species can persist. And in the case of a disease, a reproductive number larger than 1 locally means that if you have a seed at a certain number of infections, they can grow and develop. Now, that's interesting because then the stability criterion, in fact, presumes there's no mobility in there. If you look at the Ebola reports on Nature a few months back, you will see the R0b smaller than 0, so you should be safe. We're not. The local reproduction number being less than 1 is neither necessary nor sufficient for epidemic not to spread. Why? Because of mobility. If a sick guy goes into the place, unless you prevent any kind of mobility, then we'd be absolutely worse off. So the idea is that, and I hope I kind of give you the glimpse of the fact that there is a coherent theoretical framework, quite an evident one at this point, in which ecohydrological footprints or river and ecological corridors have a major impact on patterns of biodiversity, thereby potentially discussing issues like, will, in the future, large-scale water resources management plans include biodiversity preservation? That's one step in that direction. It would control spreading of migrations of waterborne disease, etc. And network structures provide hydrologic fluctuations, controls, and susceptibility. So from the peaks of infections to the local species regions, in fact, I have a feeling that's the mantra of ecohydrology. It's all in the water. And I think it also touches onto something which I think it's a moral obligation for biological and agricultural engineers or poor hydrologists like me. It is discounting the environment and rethinking social equality. I think it's truly a scientific obligation and a moral duty. Thank you. It was too long. It was too long, actually. I flooded you also beyond the time allowed, so I can be delighted to take any questions privately. Well, again, I'm not, ecohydrology is water controls on biota, okay, so generally speaking. I'm not concerned with it. There are people that dedicate their entire research life to water-controlled vegetation, for instance. That's a completely different scheme in which you have like a unit area, you have a root zone layer, and you study the balance of incoming precipitation, evapotranspiration losses, etc., and the inner dynamics of a system on controlling the biomass production, okay? That's of course, not all vegetation is water controlled. Much of it is nutrient controlled, etc. But that's a completely, it's a different thing, but still relevant in that sense. All I'm concerned is it's a way in which, models in which, if you have a problem in which you can look at whatever problem you have, population migrations, biodiversity, disease, endemic, epidemic, think if the system can be parameterized as nodes in which you have reactions, villages in which you have a disease, susceptible, becoming infected, recovering, dying perhaps, and then the certain state variables that control that thing. And patterns that connect. They can be physical, like river networks. It can be mobility patterns, spreading of infections, but also spreading of species and bringing things. If your problem can be parameterized in the form of a collection of connecting of nodes and connecting paths, then there is a lot that can be done. And in fact, even the tools that look esoteric, they're all the same and can be dealt with nicely. There will be soon enough computer codes freely available. I do believe in crowdsourcing in this case, and I think that it is our duty to produce codes that can be used in general. But the main idea you have to have is that whether you can frame your system in a system of nodes where action happens and connecting patterns, because then we have tools for you.
It's very impressive how the nature, the homogeneity in the nature and some of the processes. That makes me, lets me to think that some of the solutions that could be proposed would also be universally applicable. And what I would like to hear your thought is, are we getting toward a point where we can propose solutions that would be applicable irrespective of the scale, irrespective of the place?
Oh, it's a very interesting question, actually. And I have no magic wand, of course. All I'm saying is that, look, consider again the problem of development irrigations, sub-Saharan Africa, for instance. Quite important. I'm familiar with Burkina Faso, where we do field work, actually. There's been like maybe 150 small dams constructed in the past 10 years. Equally, I mean, in parallel to the development of irrigation networks and schemes, etc., you will see certain GDP increase of Burkina Faso and a major increase in the prevalence of bilharziose, schistosomiasis. Why? Because you expand the habitat of the intermediate host of a parasite. And then it's, unless you prevent kids to play in the water during the rainy season, which is nearly impossible, especially in the case, even supposing that, you'd be capable of. So what do you do? Now, one idea is that you can evaluate at this point, and that's my job, what would be the increase in the prevalence of a disease, of an endemic form of parasitic disease, and probably the prevalence of infected persons, the so-called mean worm burden per individual. The point is that from that point on, it's not our domain, it's the economist's domain. You have to decide whether you have a certain number of kids with a learning disability in the crucial early maturity can be compared with the GDP of increased GDP of a country. That's a different story. But unless the fact that you can be precise up to a point in predicting the prevalence of disease on what is not yet, but is in the perspective of irrigation schemes, note that empirical evidence of a correlation between water resources development and the development of a disease is documented. Then that's what agricultural and biological engineers can do, I presume. But you can say that the choice is political, the choice is ethical, the choice is humanitarian, unless economists will come up with true measures for costing ecosystem services. We're not going to be able to, if you say something is priceless, it means it costs nothing, because ecosystem services come for free usually, so they're not they're not valued. As ASBE, I think the mission should be, let's reduce the uncertainty in the consequences of what can be done, of the anthropic interventions. And let's talk about the problem embedded in that. There is a missing step, a giant one, of discounting the environment and the environmental capital you're squandering. But that's not for us.
I had one question. To what extent the discipline and the analysis has been limited by data, and how that might change as more denser, higher resolution data becomes available?
Well, it's again a very interesting question. For instance, look at mobility patterns, for instance. I can tell you that I was in the market of Carrefour outside Haiti at the height of a cholera epidemic, so all kind of in places in which, because there's no police in the place, you have like those, you're heavily escorted because they can kill you for a few bucks in the place. And I went there, I was just passing by, I saw a guy showing a telephone to a lady and get a cabbage in return. They said, what is this? The proof of payment in the poorest country in the world is given by a telephone message that's saying, payment done. Now, in a place in which we cannot construct sewage systems, the telephone got anywhere. Why am I saying this? Because human mobility now we model, gravity model, radiation models, etc. I mean, in the future, if the telephone companies would give us the positions in time, there wouldn't be any need for modeling that. It would be really big data. It would know in real time where people is going. Possibly panic-dependent patterns of mobility, because a phone is everywhere. This is just an example. Things are changing, and big data will change the way the beauty of a spatially explicit setting of node and networks is that you don't need any approximation in between. Once you get the data, you put it in. How many people move from Haiti to Lausanne, you would know on a daily basis. Of course, that changes the perspective, but this is an area in which, if I were a young guy, I would jump, frankly.
All right. Thank you very much for a very interesting presentation. Thank you.